Please welcome to the stage Runway co-founder and co-CEO Anastasis Germanidis.
Well, thank you all for joining. What an amazing turnout. I'm shocked by the amazing presentations and the amazing speakers that we had today. People talked a lot about all the applications, all the experiences, all the amazing films that they've been making with generative models. And I want to close this off by kind of talking a bit about that technology that powers all of it. And to start this off, I want to set up a framework of how to think about this evolution of media. So for the past 100+ years, media meant capturing the world. Media was recording something that happened with pointing a camera and kind of capturing a person, capturing an environment, capturing an event. And over the past 10 years, we had this big evolution that happened with generative models, where now you can describe something that doesn't exist and essentially will it into existence. And you all are familiar, I'm sure, about the rapid progress in generative models and this ability to generate increasingly realistic and increasingly compelling pieces of media. But at the same time, generative models over the past few years, they've improved a lot in quality, but they still give you a glimpse of a world without the ability to step into the world. And so the next phase of media is about simulation. It's about interacting with a live world that's dynamic and where you can move around, you can interact with people inside that world, you can manipulate and perform different tasks inside that world. And that's the evolution. The generation part was very critical to get into the simulation part. But that's how we're thinking about the evolution of the generative models and the technology that we're building at Runway. And I'm going to split the talk in two parts. One is about all the progress that has happened in generation, and then all the things that are coming up ahead in simulation. So there's been a lot of progress in generative models over the past few years, and it's easy when you see where the technology is today to miss how fast the progress has been. So it's always very helpful to just look at where the models were and where the technology was just even like half a decade ago. And so we often show this film inside Runway. It's something that every new member of the team watches. It's a film that my co-founder Alejandro made back in 2021, and it basically, we call it the Orange, and it's an attempt, like a very honest attempt, to piece together the image models of 5 years ago and just trying to make a film out of them. And you can see how pixelated, crude it looks, but it was still a glimpse of something bigger. We call, the three of us co-founders, we call ourselves failed filmmakers, and this is, I think, a good indication of that. So what changed? There's a few different factors in how quickly the models have evolved, but one very critical piece of the story is this idea of scaling laws. It's a really beautiful idea that the model architectures and that have not dramatically changed from what we had in 2021. Of course, there's been improvements in algorithms and some of the aspects of training those models, but a big piece of the puzzle is this idea of scaling laws, which is you can add more compute and you can add more data into the models, and they're going to predictably improve, even if you keep the architecture exactly the same. And scaling was a big part of the past 5 years, not the whole story, but just to look at the progress that we've made since then. That was 2021. In 2022, you had the image generation models that just starting to become really good. And we started to experiment with how can you take the outputs of those models and make something, kind of animate them in some form or another. And then 2023 was a big moment for us when we released Gen 1 and Gen 2, our first video models. And that was, a lot of it was just commitment to really scaling kind of the training of video generation models. Who here has used Gen 1 or Gen 2? Wow. Well, I'm sorry about that. It wasn't they weren't the easiest models to work with, but again, like they were really, really fun to play around and really giving a sense of like this was something new, a way of working and a way of creating media that didn't exist before. And then 2024 came Gen 3, again, a big improvement in the ability to dynamic camera motion in terms of human behavior. And finally, 2025, Gen 4.5, our latest base model that we released at the tail end of the year. So I think that the improvement is pretty obvious. One nice thing about video models and image models is you can immediately tell with your eyes when something is better. But it wasn't enough. And as you heard from so many amazing speakers, that all the kinds of workflows, all the things that they've built on top of those models, all the kinds of applications, now that we had a good recipe for quality, the next piece was consistency and control. And the way we tried to solve it was by building a very general approach towards control. Something that you could take all the lessons that we've learned from language models, this ability to have the same model that can do translation, it can do coding, it can do creative writing, and have the same approach in how we thought about video models. You had a single model that could give you new camera angles of a scene. It could add objects, remove objects. It could stylize a scene. And I think that was a big unlock in terms of thinking about video models the same way that we thought about language models, where you could have this general approach and the model understands how you're trying to transform a piece of footage. And some of the capabilities are quite astounding in terms of the ability of the model to understand what's inside a specific video and transform it. So remove things, kind of perform different kinds of control, precisely direct the motion in the scene, or kind of stylize and kind of take a untextured 3D scene and make it into a photorealistic output, which is quite a big unlock for combining traditional workflows in 3D with generative models. And that aspect of combining existing workflows is something we've never been religious or dogmatic around. Everything needs to be generated end to end. It can't be combining the best of both worlds, combining the best of what works in traditional workflows and traditional filmmaking, and the aspects that generative models do really, really well. And I think that continues and will continue to be part of the story and how we think those models should be used.
AI video generation changes how...
Before I move to this, we had quality, we had control. The third piece, which I think is very important and somewhat underlooked as we move into generative AI, is latency. You have a completely different tool when you have a tool that works, gives you a response in 1 minute versus a tool that gives you a response in 10 seconds versus a tool that gives you a response in a second. It's a completely different experience because a tool that gives you a response very quickly feels like an extension of your mind in a way that the tool that takes a while to generate and give you an output does not. And speed can be very often underlooked. And it didn't make sense necessarily to focus on it when the quality was at the level of the orange film that I showed. But now that we have this level of capability where the quality is quite good, it makes sense to focus on getting those models to be as fast as possible so that they feel real extensions of your mind, and you can feel that you can iterate with them, like they can work as fast as your mind works. So I want to show a collaboration that we did with NVIDIA to build a real-time version of Gen 4.5. This is a short video that kind of explains it and shows it.
AI video generation changes how scenes are created and directed, but can't scale at the speed AI simulation and creator workflows require. Just 3 months ago, Runway's Gen 4.5 generated scenes in minutes. Now, their new model, accelerated by Vera Rubin, generates them instantly. That speed changes everything. Instead of waiting for a render, scenes can be directed while they are generated. With just a simple prompt, new frames appear. When new direction is given, the scene updates again in real time. Video generation becomes a live creative loop.
So this is Gen 4.5 real time. It's a variant of our model that's trained to essentially generate frames in real time and have time to first frame be under 100 milliseconds. So that means the moment you type in a prompt, you press generate, the first frame of the output is generated in less than 100 milliseconds. And we're very proud of this model. It's still early days, but we're able to get very close to the performance of the original base model. And we expect real-time generation to be a big part of how people use video models in the future. And that allows for a completely new kind of iteration. It takes more time to type in a prompt than to get back an output. And you can explore ideas much faster than you could with a regular kind of iterative workflow. So I talked about quality, I talked about control, and I talked about latency and efficiency. I think at the end of last year, we tried to take a step back and kind of all the progress that's been made in video generation. And we ran this user study where we asked participants of the study to take a look at 2 videos. One is generated, one is real, and pick the one that's real, or pick the one that's generated. And we found out that actually less than 10% of participants could reliably tell the difference between real and generated video. And that points to something, a fundamental transformation in what those models can do. In order to generate video that's indistinguishable in many cases from real-world video, they need to simulate and understand so many aspects of the physical world. And that brings me to kind of the second section of this talk, which is about this idea that video models are also world simulators. And it's really, to some extent, it's just a different way of looking at the same underlying technology and same underlying models. Because in order to predict video well, in order to predict what happens next, given a first frame, the model needs to build some understanding of the world and its dynamics, and its how physics, it needs to be an understanding of physics, and it needs to be an understanding of how humans move in a scene, so many aspects of the things that we take for granted. And what's amazing to me is that the same models that are used for all kinds of amazing creative applications, there's the same models that we can use for simulation that's useful in a lot of different new areas and industries. One really important piece as well is that video is not just, it's a very general representation as well. So that means that video is not just the human scale kind of observations of the world. It's the video, the footage that you shoot with a camera. But you can also represent as video a lot of observations that come from different scales of the world, from like microscopic level to kind of astrophysics level, and also digital observations. So that means kind of the pixels that come from in your screen of like as you're playing a game, as you're interacting with software. So it's a very general representation of both the real world and also the digital world. And so when we think about video models, they can be trained on all kinds of observations of the world that go beyond what we can see with our eyes. And we think video models and world models as a new foundation for intelligence and a new foundation for software that understands and can simulate the world. It can simulate environments, it can simulate how autonomous systems interact with the world, and you can simulate kind of conversation and behavior as well. And not to get too technical, but it's actually not a big departure from how we've been building video models. The main difference is with video models, you're generating an entire video at once. You're generating all the frames at the same time. With a world model, it's an autoregressive model, which means frames are being generated one or a few at a time, and you can continuously interact and change what happens. So interactions can be a lot of different things. It can be moving around in space. It can be interacting with a character. It could be controlling an object. And these are some of examples of the world models that we've been working on. So this is GWM Worlds, which is a world model for navigating an environment that can not just allow you to move around a static environment, but actually it's a very live environment that can be dynamic, where you can kind of manipulate and take actions in it. And we're very excited to show you more of GWM Worlds in the coming weeks. We're particularly excited about the applications of our models in robotics, which is not the first thing that you would think a creative tools company and video model company would work on, but it's something we actually saw. It was something that robotics companies and labs came to us last year, asking us to use our models in their own research, in their own work. And the reason why video models can be so powerful in robotics is that robotics is very data bottlenecked. It's very time-consuming and expensive to collect data to train robots, and you're really bounded by the hardware that you have available. And hardware does not scale in the same way that software does. But being able to generate footage from video models, examples of robots performing tasks, examples in different environments, in different settings, can massively accelerate how fast you can train those models. And one very important piece of that is the ability of those models to simulate failure. As you can imagine, video models are trained much more on successful examples of things than failed examples. If you go to Runway and generate a video of someone scoring a goal versus failing to score a goal and missing, it's probably going to do a better job at the example of scoring the goal, because there's just much more video out there of humans doing something successfully. So it's actually a surprising challenge to get models to simulate failure as well as they simulate success. But it's very critical as we deal with systems that have to, as we use those models to train robots that need to recover from failure. They need to be able to simulate success as well as need to be able to simulate failure. And one of the early findings that we have is that actually our video models can be quite successful simulators. And by that, I mean that you can simulate how a robot performs inside our video model and world model, and have the robot perform the same action in the real world. And if the robot succeeds in simulation, it will likely succeed in the real world. If it fails in simulation, it will fail in the real world. And so that means that you can test how robots perform much faster than you otherwise could. And you can simulate things that are very difficult for more traditional simulators to do. Because video models have been trained on a vast number of videos of observations of the world. And they can simulate things in they can simulate things that are traditionally very difficult for 3D simulators to do, and you don't require any manual effort to build environments or to describe the physics of every object, because a video model already has that knowledge inherent in it. So I described kind of the journey from capturing reality to our efforts to build great models for generating reality, and finally to building simulators of the world. I think we're very early in this journey to build great simulators of the world, and it's still, to my mind, very underlooked what are all the possible applications of them. But we're seeing very promising early indications of that. And I'm sure by the time we run this summit, hopefully next year, we'll have way more to share as well. Thank you for your time.